So the intermediate value theorem is what we were talking about at the end of class last time. I had time to just barely introduce it. Thank you. And it just basically tells us if we have a polynomial with only real coefficients, that's going to be all of our polynomials. So you can just say we have a polynomial, just one of our polynomials we've been working with. And you know that two x values give opposite signs. In other words, if you know that you have ordered pairs, one above the x-axis and one below the x-axis, then you know in between there somewhere you have an x-intercept. That's what this is trying to tell you. So we talked about this at the very end of class last time, where we know that if you have a graph or something that's a polynomial, even if you can't see the whole thing, because these things are continuous, we know there is at least one x-intercept between x equals 3 and x equals 7. And why do we say at least one? Why do we say at least one? Why don't we just say there's exactly one?
Because it can still drift back up and down.
Yeah, there could be more than one x-intercept in there. The graph could do something, like this, and we can have more than one x-intercept in there. So we don't want to say there's exactly one. We want to say there is at least one. Now, normally we don't do this with a picture. Normally what happens is you'll have some sort of function, and you'll plug a couple values into it, like this. You'll know that f of x is a polynomial, and you'll know something like f of 2 equals 4, and f of 5 equals -3. And what you'll notice is 2, 4 is above the x-axis, and 5, -3 is below the x-axis. So the conclusion we make is f of x has at least one x-intercept between x equals 2 and x equals 5. Even without a picture, if we know we have an ordered pair above the x-axis and another one below the x-axis, we know somewhere in between those two x values, there's at least one x-intercept. The intermediate value theorem doesn't tell us where it is. It doesn't tell us how many there are. It just guarantees there's at least one, which is why a lot of people don't like this theorem too much. They're like, well, what does it tell you? Well, it's basically just a conclusion we'd want to make on our own, that, yeah, if we're above and then later on we're below, somewhere in between we had to hit that x-axis. So I don't know how many x-intercepts. And I don't know exactly where they are. I just know they're between 2 and 5. For that example. And we don't want to ask too much of the intermediate value theorem. There's some things it can't tell us. For instance, here's another picture of a polynomial, but I'm going to remove a piece from it. Is there an x-intercept in between those two numbers?
No. Zero.
There's a really good answer to this one. It's our favorite answer to give in math class, and it's actually right. I don't know. Is it possible that this thing just goes like this? Could that happen?
Yeah.
Is it also possible that it could go like this?
Yeah.
So we don't know. So if both ordered pairs are above the x-axis or below the x-axis, like they are in that picture over there, then the intermediate value theorem, IVT, tells us nothing. And the correct thing to say is, I don't know. I don't know if there's an x-intercept in there. There could be, but I don't know for sure. I don't even know how many there might be. There could be 1, 2, 3, 4, doesn't matter. Because we have bounces and crosses. We don't know how many we have, whether it's even or odd. So, if you're ever working with an example like this, you have a polynomial, and you know that when you plug in a 1, you get a 4, and when you plug in a 7, you get an 8, and someone says, is there an x-intercept between x equals 1 and x equals 7, what is the best answer you can give them?
1 and 7.
Is there an x-intercept between 1 and 7? I don't know. I don't know, because both these points are above the x-axis. Maybe there is, maybe there isn't. Everyone see that? We just don't know. I don't know because both points are above the x-axis. So, here's what I came up with for you. When someone asks you to use the intermediate value theorem, there are several things you might want to try and tell people. You might want to say that the intermediate value theorem guarantees at least one x-intercept between the two given x values. That's what you say if the y values are such that one is positive and other is negative. If you put two x values into a function and you get a y value that's positive and a y value that's negative, then you know there's at least one x-intercept in there. But you never get to say there's exactly one x-intercept. You never get to say there is no x-intercept. You might get to say, I don't know. This tells us nothing. And that's if both y values are positive or both are negative. So you'll see that when you do your homework, everyone. You'll see the intermediate value theorem in action. But the big thing I want to stress to you is that these two answers that I've crossed out are never correct. Never. This one is sometimes correct. This one's sometimes correct. But these two, if this was a multiple choice problem on a test and these two were choices, you could cross them off right away and say there's no way that's ever the answer to this problem. What do you think about that, class? Is that okay? Intermediate value theorem? All right, we got one more thing to do and then we'll be done with section 3.4. Using arrow notation, so we have four different types of end behavior a polynomial could have. In other words, which way were the arrows tending as we went really far out to the left and really far out to the right? But one way to describe this is using what we call arrow notation. Unfortunately, that does not refer to these arrows I just drew. What this refers to as describing what's happening using arrows and infinity language. Let me show you what I mean by that. This one right here. This is a way to describe that end behavior using what we call arrow notation. Now, does anyone remember how I told you we say that out loud, the arrow out loud? Approaching or approaches, yes. The word approaches or approaching. So what we say is as x is approaching or approaches infinity, as we go really far out to infinity, the function itself is going up to infinity. As we go really, really far out negative infinity in this direction, the function itself is also going up to infinity. Remember, this is infinity. This is negative infinity down here. This is negative infinity down here. This is infinity up here. So what you're saying, as we go really far on one axis, what's happening on the other axis? Is that okay with everyone so far? So let's try this one. This one would be as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches negative infinity also. And if you're thinking about what we're doing is the x is just telling us what axis we're looking at, and then infinity or negative infinity is telling us what direction we're going, up or down. So if you're talking about x approaching, you're talking about we are on the x-axis, and you're talking about y approaching, we are on the y-axis. If you're talking about infinity, you're either talking about right or up, right for x values, up for y values. If you're talking about negative infinity, you're talking about left for x values or down for y values. So, class, why do I bring this up? Because you have a homework problem in section 3.4 that's going to use this type of notation. I wanted to show it to you. So you weren't messed up. It's something we've already talked about, but like many things in math, it's just a different way of talking about it than we might be used to. Write down the equation of a polynomial with the following properties. As x approaches negative infinity, y approaches infinity. As x approaches positive infinity, y approaches negative infinity. That right there is what that tells me. I'm supposed to write an equation that has that end behavior. So it's not bad once you understand what it means, but like anything else in math, if no one explains to you what the notation means, it's a very frustrating problem. Does that look okay to everyone? We're going to do a little bit more arrow notation in section 3.5, so I just want to make sure everyone's cool with it in this section before we move on to it. It's slightly more complicated in the next section. All right, well, that is the end of section 3.4, so now you should be able to complete that homework for yourself. So good luck with that. Let me know if there's any problems. Send me an email, talk to Rachel, or talk to me, let us know if you have any difficulty so we can help you out. So I won't lie to you, rational functions are tricky enough. We could actually do a whole unit just on rational functions. So what we're going to do, everyone, is this is going to be an introduction, but still a lot of information. This is another type of function we're going to look at, and it's got its own set of rules. And they're tricky, I won't lie. I'm not going to try and scare you all today, because I don't want to do that. But I will tell you these are tricky. There's a lot going on with these rational functions. What is a rational function? It is a polynomial divided by another polynomial. The polynomial on top could just be a number. So a rational function is a polynomial divided by another polynomial. For instance, that's a rational function. Polynomial on top, polynomial on the bottom. That's a rational function. Polynomial on top, polynomial on the bottom, because we do say that the polynomial on top is allowed to just be a number. But these will be polynomials on top and polynomials on the bottom. You still can't have radicals, you still can't have absolute values. So this right here, 7x plus 2 over the square root of x, is not considered a rational function. You can't have a square root. This right here, x, absolute value of x over 3x plus 7, that's not a rational function. We're not allowed to have absolute values in our rational function. So it is just going to be what we were working with in the previous sections, a polynomial on top, a polynomial on the bottom. We don't, well, let me say this. We need at least one x in denominator, or we just have a polynomial. If we have something like that, that's not really a rational function in the sense that we're going to be working with, because this is technically more of a polynomial, because you could write it like this. So that's why I say we need to have at least one x in the denominator if we're going to call these things rational functions. Otherwise, they're really just a complicated looking polynomial. But please remember, and I know it's already a lot of information, please remember, you are allowed just to have a number on top, but we won't just have just a number on the bottom. All right. Because rational functions have x's in the denominator, the domain might not be negative infinity to infinity, because we can't plug in a number for x that causes division by 0. When we first learned about domain in this class, one of the first things I told you was we cannot divide by 0. Rational functions are going to have x's in the denominator. That's different from polynomials. They're going to have x's in the denominator. That means our domain might not be negative infinity to infinity, because we can't plug in a number for x that will cause us to divide by 0. So if someone gives us this rational function right here, which is not a super complicated one, but it's still a rational function because it's a polynomial on top and a polynomial on the bottom, what number are we not allowed to plug in there? Negative 4. So the domain for this one is everything except negative 4. And suddenly we're back to using interval notation for our domain. With polynomials, it was great. You can plug in any number you want at any time. With these, we do have to be careful not to divide by 0. What two numbers must I kick out? 7 and negative 3. Does it make a difference which order I jump over them? In interval notation, does it make a difference when I write my domain? You have to do it in order. So it has to be this, everyone. It has to be the negative 3, then the 7 to infinity. You have to write it like that. If you switch the locations of your 7 and negative 3 on that, you're not going to have the right answer. Because interval notation, you're like looking at the number line as you go from all the way to negative to infinity, and you have to jump over the numbers as you go left to right. So it does make a difference. If you were just to write x doesn't equal, those could be written in either order, but interval notation must be in order. How about this one? H of x equals 5x plus 1 over x times x plus 5. Don't forget what you know about polynomials. What I'm basically asking you right now are what are the zeros of the denominator? What are the numbers that will make the denominator equal to 0? What numbers make the denominator equal to 0? 0 and negative 5. Very good. Jump over negative 5 first, then jump over 0, then on to infinity. Yes. What we are doing, everyone, is with a rational function, we need to let people know, because there's a possibility you might divide by 0 because there's x's in the denominator. We need to tell people right off the bat what numbers we need to exclude by writing the domain. And the domain is actually all the numbers you're allowed to plug in, skipping the numbers you're not. Be aware of this tricky situation, though. Does anyone know what the domain of this rational function is? This is not a trick question per se, but it does have a tricky domain. We got to kick out numbers that make the bottom equal to 0. Does everyone agree with that? The only numbers that will make the bottom equal to 0 are imaginary. Do imaginary numbers enter our thinking when we do domain? No, so here's the rub, everyone. There are no real zeros for the denominator, so the domain is negative infinity to infinity. Since the only numbers that would make the bottom equal to 0 are imaginary, and imaginary numbers don't enter our thinking when we're talking about domain, this one actually has a domain of negative infinity to infinity. In other words, you can plug any real number you want in here, and you'll always get an answer back. So it is tricky, and we've done this kind of thing before, finding domains, but it's been a while since we've been doing quadratics and polynomials for so long that we kind of stopped doing this for a while because our domain was always negative infinity to infinity. So we got to retrain ourselves to remember, never divide by 0, and make sure you write a domain that kicks out the numbers that cause division by 0. Takes some practice, of course it does. Does everyone understand the concept though, even if you need to practice a little bit more on your own? All right, so don't divide by 0. Jump all real x values that make denominator 0. All right, let's talk about what a rational function looks like. Graphs for rational functions often look very different from polynomials. Now, if I can stay on schedule today, and that's on me, not on any of you, so don't worry about it, but if I can stay on schedule today, I'm going to have you graphing this function before the day is over. A polynomial over a polynomial. The graph for this looks like this. So big. This is what the graph of that rational function looks like, everyone. And I'm going to have you doing this before the day is over today. I'm going to teach you how to draw this graph. Just in case you're curious about a couple things about this graph, let me give you a little bit of vocab and just a little bit of knowledge about it. First of all, you can see the graph has 3 different pieces. That's one thing we want to notice about it. It has 3 different pieces. The other thing I want you to notice is the dashed lines are called asymptotes. We're going to talk about those today. The dashed lines you see on there, the dashed lines in green, are called asymptotes. And what else do I want to say about this thing? 3 different pieces, dashed line, domain is not negative infinity to infinity. And as we all know, everyone, is this a parabola right here? Is this a parabola? Where do parabolas come from? What do we have to draw to get a parabola? What graph or what equation? A quadratic. This is not a quadratic, it's a rational function. So this is not a parabola. Okay, so I'm going to teach you how to graph one of these things. This is what we're going to build up to today. And at the end of today's class, we're going to draw this exact same graph, but we're going to do it by hand without any help from a computer. It's going to be pretty sweet. I mean, mathematically, you don't have to be the most excited about it, but that's what we're going to be getting to today. Rational functions could have any number of what we call vertical asymptotes. Those dashed vertical lines are called vertical asymptotes, and rational functions could have any number of those. In other words, they could have 0, 1, 2, 3, 4, 5. You could draw a rational function that had 20 of them. We're not going to do that, but you could. Rational functions have 1 or none horizontal asymptote. They have 1 or they don't have 1, is the idea. So if you look back at the graph for a second, these 2 green ones here, oh, they're all green, but these 2 are called the vertical asymptotes. This one's called the horizontal asymptote. You might have a horizontal asymptote, or you might not. But you could have many vertical asymptotes. The horizontal asymptote is a different type of end behavior. If you think about how our polynomials had end behaviors, they either went up on both sides, down on both sides, up on one side, down the other, or vice versa. If you look at this graph up here, you'll notice it's not going up or down as we go to the left and right. It's getting very, very close to that horizontal line. It's another type of end behavior. We did not see this with polynomials. We will see this with rational functions. Okay. Rational function graphs have one more piece than the number of vertical asymptotes. Don't let this one mess with you. If you look above, we see 2 vertical asymptotes. We see 2 of those dashed vertical lines. And how many pieces does the graph have? How many different parts of the graph do you see? 3. That's all that means. Well, we see 2 vertical asymptotes, 3 pieces to the graph. Vertical asymptotes are directly related to values kicked out of the domain. So it almost seems, class, and this is the case, it almost seems if we can find those vertical asymptotes, if we can find where those dashed vertical lines are that kind of break up the graph, and we can find that horizontal asymptote, both of which I'll teach you how to do today, we can actually start sketching one of these things. And once again, I'm sorry because there's so much information in this, and I've been teaching this class for a while, so I've worked very hard to find the best way to present it to you, and the best way does seem to be to present you with a bunch of tools building up to what we're going to be doing. But it is a lot to take in, I know that. So bear with me and we'll get there. We had those basic functions in our first unit. X squared, x cubed, cube root of x, square root of x, absolute value of x. Here's kind of another basic function. It's the most basic of all rational functions. This is kind of the simplest rational function you can write, 1 over x. It is sometimes called the inverse function. It is sometimes called the reciprocal function. But it's 1 over x. What's the only number you're not allowed to plug in there? 0, yeah. It has a domain of negative infinity to 0 and 0 to infinity. Harder to find, and you wouldn't necessarily know this just by looking at this, everyone, but the range of it is actually also the same. I'm writing this little note, harder to find here, so you don't wonder later, how did I know that? I know that because I've worked with this function before. You're not supposed to know that just by looking at it. Here's what it looks like in a bunch of pictures before class today. I'll draw some myself because I want you to learn how to draw them, but for this introduction, it's kind of easier for us to look at some pictures that are pre-done for us. So this is what the graph looks like. It does have arrows that keep going. The program I use, though, doesn't put those on there. This is a rational function. Now, I know it might be kind of hard to see from where you're sitting, everyone, but if you look carefully at it, you can actually see that this has a horizontal asymptote and a vertical asymptote. They're just right on the axes. I don't know if you can see those green dashed lines. I'm sorry if you can't. But this does have a vertical asymptote right here, and it does have a horizontal asymptote right here. Does anyone remember what the equation is that lies directly on top of the y-axis, what that's called, the equation? Is that x equals 0 or y equals 0, the vertical one? That one's x equals 0, a little counterintuitive. And the one down here is y equals 0. It's got those two asymptotes. But if it's got one vertical asymptote, we'll notice that the one vertical asymptote means the graph has two pieces. And one reason I wanted to show you this graph is I wanted to show you that what a graph does, what a rational function does, is it sort of hugs its asymptotes. Now, you're not going to see this word in the book. Rational functions hug their asymptotes. But it turns out they never touch a vertical asymptote. And even though this one does not, some rational functions do touch their horizontal asymptote. So rational functions hug their asymptotes, but they'll never touch a vertical asymptote, never. I'll remind you of that as we go through our class today. They never touch a vertical asymptote. And although this one does not, it is possible for a rational function to touch its horizontal asymptote. What else do I want to tell you about this? Well, it still follows the same rules that any function does in that you can plug in a number and get a number back out. Everyone, we can't plug a 0 into this function. Are we allowed to plug a 1 into that function? What do you get if you plug a 1 in there? What's 1 over 1? 1. Yeah. F of 1 equals 1. And yes, the ordered pair, 1, 1, is on the graph. What if you plug a 2 in there? What will you get? What's 1 over 2? 1/2. And yes, this does have the ordered pair, 2, 1/2. If you plug in a -3, you'll get -1/3. Good, Stephen. So that rule hasn't gone away. No matter how bizarre or weird looking a function is, it still works, and if you plug in any number in the domain, you will get a number back out, and that is an ordered pair on the graph. So if these things start to spook you, please remember that they do follow that rule. By the way, if you plug in a 1/4, do you know what you'll get? Do you know what 1 divided by 1/4 is? It is 4. Yes, good. Right now they seem kind of daunting, but we will tame these things today. We'll show them who's boss. All right. Steps for working with and graphing a rational function. Here's what you need to do if you want to work with a rational function. You first figure out its domain. You first find out what numbers you need to kick out. Use interval notation to jump numbers that cause division by 0. Vertical asymptotes. Vertical asymptotes how many? They appear on graph as dashed vertical lines. So we're going to figure out how many of these vertical asymptotes one of our rational functions have, and then we're going to put them in as dashed vertical lines. I will tell you how to figure out how many we have in a moment. Horizontal asymptote. Do we have one or not? You never have more than one horizontal asymptote. There either is one or there isn't one. It will show up on the graph as a dashed horizontal line. Horizontal asymptote, you either have one or none. Vertical asymptotes, you have 1, 2, 3, 4, as many as you want. Just like with polynomials, we are concerned about the x-intercepts, or the y-intercept if there is one. Sometimes we find extra points. And then we can graph it. My job here in the next few minutes, and by next few minutes I mean maybe the next half hour or so, and we will take a break in there, don't worry, but my job is to explain to you how to look at an equation of a rational function and figure out all this. That's what we're doing. That's where we're going to. Just like polynomials, we needed to learn the rules before we could graph a polynomial. When we were doing parabolas, we needed to learn about the rules before we could graph a parabola. If we're going to graph a rational function, we need to know all the rules. We need to know the vocab, otherwise we don't have a chance of graphing it. All right. So, we already did domain, vertical asymptotes. Vertical lines, dashed, up and down, forever, occur at x values removed from domain. That's what your vertical asymptotes are, everyone. They are vertical lines that are dashed, and because they're vertical lines, they will be x equals. And they occur at the exact same x values you remove from the domain, the exact same x values. So, if someone said to me, Steve, there's my rational function, then this is what I would say to them. Your domain is everything except -3 and 5, and your vertical asymptotes are x equals -3 and x equals 5. Then I would go over to the coordinate system, and at -3 and 5, I would put in 2 dashed vertical lines. Can we do that? If you can find domain, you can do it. If you can find the domain, you can do this. What 2 numbers am I kicking out of the domain? You're just looking at the bottom right now, right? You're not even looking at that x minus 5 on top, and you shouldn't be. Yep, 0 and 2. So, domain (0 and 2), vertical asymptotes, x equals 0, x equals 2. If I was drawing this one, I put in my vertical asymptotes like that. Can you see why you could have infinitely many on this, or as many as you wanted? Because all I'd have to do, if I wanted more, is just go like this. X minus 1, x minus 2, x minus 3, x minus 4. That's why I say we can have as many as we want. Because if I just want to keep adding factors to that denominator, I can just keep adding vertical asymptotes. There are no real numbers that will make that denominator equal to 0. There are no real numbers for the domains negative infinity to infinity. If your domain is negative infinity to infinity, that directly tells you that there are no vertical asymptotes on your graph anywhere. The only way you can have a vertical asymptote is if you kick a number out of the domain. If you don't kick any numbers out of the domain, you have no vertical asymptotes. Now I have to tell you something, just so you don't think I'm a liar, and that is this. Vertical asymptotes get more complicated if we have common factors canceling in the numerator and denominator. This will not happen in Math 121. Except maybe in one homework problem, and I'll tell you how to deal with that later. But class, in general, these vertical asymptotes do get more complicated if you have factors that start canceling. In this class, we're not going to see that. And there might be one homework problem where that comes up, and I will tell you how to deal with that, don't worry. But it does get more interesting when factors start canceling. So just keep that in mind. But for this class, Math 121 in general, we just say if we kick it out of the domain, it's a vertical asymptote. Okay. Let me do one more thing here. Yes, I'm going to finish vertical asymptotes, then we'll take a break. Does that sound okay to everyone? All right. A vertical asymptote causes your graph to approach infinity or negative infinity as we get close to that x value. What a vertical asymptote does, everyone, is as the graph gets close to a vertical asymptote, it's going to make a choice. It's either going to kind of shoot up that vertical asymptote or down that vertical asymptote. So if you look at these pictures up here, what I wanted to show you was I showed 4 different graphs, each with one vertical asymptote. And what you will notice is that as the graph, the black part, gets close to the green dashed line, it either goes up or down the vertical asymptote. Sometimes it does the same thing on both sides, sometimes it does opposite things on either side. It could do any one of those things. But that's how a graph behaves when it gets close to it. It never touches vertical asymptote, it just hugs it. By hugging, I mean gets really close. So what I did on this one, class, and this is going to get a little bit sticky, but I put my vertical asymptote for all of these at x equals 3. All of these have their vertical asymptote at x equals 3. And here's what I want to say. You see, we want to say, as we get really, really close to 3, what does the graph do? Let's start with this one over here. As x approaches 3, the function goes to infinity. In other words, as we get really, really close to 3, the graph goes up. Everyone see that? As you get close to 3. This one over here, as x approaches 3, the function goes down to negative infinity. As we get really, really close to 3, the function shoots down, goes down forever. Why are these two going to give me some problems? Can anyone tell me what I'm going to have an issue with right now?
You're going to have to do 2 of them, right?
I'm going to have to do 2 of them because it's doing different things on each side. Does everyone see that? So everyone, see what I want to say is x approaches 3. On one side we go to infinity, and on the other side it goes down to negative infinity. Does everyone see the issue there? As we approach 3, as we get really close to 3 from either side, one way it goes up, one way it goes down. So here's how you deal with that. And once again, I apologize for all the nasty notation, but this is how we do it. This is how we deal with it. That little symbol that I put after it almost looks like a power. It looks like I wrote 3 to the negative power or 3 to the positive power. What that indicates is it indicates what direction you're coming from on the x-axis. So everyone, point in the direction of the negative x-axis. Where is it? Just point. You got it. This way, right? Over here is our negative x-axis. That's the left side. That's the negative direction. What this means is as we approach 3 from the negative direction. As we approach 3 from this side, we go up to infinity. As we approach 3 from the positive side, we go down to negative infinity. The way you read these out loud is from the left and from the right. So this one, as we approach 3 from the, oops, let me do it the same way I did the other one. As we approach 3 from the left on this one, the graph goes down to negative infinity, and as x approaches 3 from the right on this one, function goes up to infinity. Those take a little while to digest. But it's just a way of saying mathematically, it's our mathematical notation, rather than me coming in here and saying, you see how we get really close, and then we shoot up forever? This is just the way we write that mathematically. As we get really close to 3, as x approaches 3, the function goes up to infinity. That's what mathematical notation is for, so we don't have to get all wordy. All right, I think that will work for vertical asymptotes. So let's, does our rational function have a horizontal asymptote, or does it not have a horizontal asymptote? It either has one or it doesn't. If it does, it will be y equals a number, and it will be a dashed line that goes left and right forever. The function will get very close to it, to this horizontal asymptote, as x approaches infinity and x approaches negative infinity. It may even cross the horizontal asymptote. I'll just leave it at that. It may even cross the horizontal asymptote. You can touch one of these. You don't always touch one of these, but you can touch one of these. So what this is, everyone, is it is a type of end behavior. It is a type of end behavior that rational functions, the ones we're doing today, rational functions can have, but polynomials can't. Polynomials didn't have these horizontal asymptotes. We've never talked about them before. It didn't have them. But a rational function, the new functions we're talking about today, could have these. So what I did, everyone, was I actually, for this one, I didn't draw these myself. I got on the internet and Googled horizontal asymptotes just so I could find some pictures for you, and I found 2 I liked of horizontal asymptotes. So here's one that's right on the line y equals 0, right on the x-axis. And what I want you to notice is that right here, the function does cross over the horizontal asymptote. That is not a bad thing. You're allowed to do that. But the other thing I want you to notice, which makes it a type of end behavior, is as x approaches negative infinity, as we go really far out to the left, the function gets really close to the horizontal asymptote. It gets really close to 0. This is just going to start hugging that asymptote all the way out. And if you go in this direction, as x approaches positive infinity, the function will approach 0. It will get really close to that horizontal asymptote. So rather than going up on both sides, or down, or a mix like that, what these do, some of these rational functions, is they instead get really close to a horizontal line as you go really far out. Here's another one, another horizontal asymptote. This one is y equals 3. Once again, you will notice that we crossed right here. And for this one, as x approaches negative infinity, the function itself gets really close to 3. And as x approaches positive infinity, the the function itself gets really, really close to 3. But the reason you can't have 2 of them is because you can't get close to 2 horizontal lines at the same time. So remember, rational functions have one horizontal asymptote or no horizontal asymptote. And if no horizontal asymptote, end behavior is similar to polynomials. In other words, if it doesn't have one of these horizontal asymptotes, we'll have a similar end behavior to a polynomial, either up on both sides, down on both sides, up on one, down on the other, like that. So we want these horizontal asymptotes because it's just a new type of end behavior. And maybe they're right on the x-axis and maybe they're not. So my job here in the next few minutes is to teach you how to find out if your rational function has one of these or not. Last note I'll make here, just so we're absolutely clear. For rational functions, the graph gets close to the horizontal asymptote in both directions. In other words, class, you're not going to get close to a horizontal asymptote on one side and not on the other side. All right, that's what they are. It's a type of end behavior. Does your rational function have one? Check out the polynomials on top and bottom that make up your function. What is the degree of each? The way you decide if your rational function has a horizontal asymptote is you look at the polynomial on top and the polynomial on the bottom that make up your rational function. And if they truly are polynomials, one on top and one on the bottom, then each one of them does have a degree. So just look at the polynomial on top of the rational function. What's its degree? 2. Highest power is 2. What about the one on the bottom? What's its degree? 2. If the degrees match, horizontal asymptote is y equals the leading coefficient of the top divided by the leading coefficient of the bottom. What's the leading coefficient on the top? -10. What's the leading coefficient on the bottom? 2. What's -10 divided by 2? That's your horizontal asymptote. You look at the degree on top, you look at the degree on the bottom. If they match, you divide the leading coefficients, and you've got your horizontal asymptote.
What if they don't match?
Oh, we'll get to that one, don't worry. It's a great question. Because there's kind of 2 ways they might not match. Either the one on top is bigger or the one on the bottom is bigger. Does everyone agree with that? If they don't match, that one of those 2 things is going to happen. So, let's say you have this. Do a different function here. (7x squared minus 8x over 9x cubed plus 2). What's the degree on top?
2.
2. What's the degree on the bottom? 3. If degree on bottom is larger, then y equals 0 is your horizontal asymptote. Every time, guaranteed. You don't even need to do any division. You're just done. That's right on top of the x-axis, everyone, but we write y equals 0. We write the equation. If the degree on the bottom is larger, you're done. It's just going to be y equals 0 every time. And what's our final option? 7x to the 4th minus 18x over x plus 9. Degree 4 over degree 1. If degree on top is larger, you don't have a horizontal asymptote.
Even not 0?
What's that?
Not 0?
No, the other one was 0. That's if the degree on the bottom was larger. If the degree on top is larger, you don't have a horizontal asymptote. And the end behavior will be similar to one of the 4 types of end behavior of polynomials. Okay. That's actually it for horizontal asymptotes. It's only one you have to worry about. You either have it or you don't. If your degrees match, you do a little division problem. If your degree on the bottom is larger, you're done. It's y equals 0. If your degree on top is larger, you have no horizontal asymptote. And we don't see a lot of these in this class. You still need to understand that. You still need to understand how to tell if there's no horizontal asymptote. We actually don't see a lot of those in this class. Most of the ones we're going to look at, check out behind you there. Most of the ones we're going to look at have a horizontal asymptote. All right, moving our way through the process, we actually only have 2 things left. And I think they're actually the quickest things to find. X-intercepts and the y-intercept. X-intercept. Values in domain that make the top only equal to 0. An x-intercept is a value that makes the top equal to 0. It has to be a real number, so that's why I say in the domain. So in other words, it's the real zeros of the numerator. The y-intercept, and I'll give you an example of both in a second. The y-intercept is if 0 is in domain, in other words, you didn't kick it out, plug 0 in for every x, top and bottom, to get your y-intercept. X-intercepts, the numbers that make the top equal to 0, as long as they're real and they're in the domain. Y-intercept, plug 0 in everywhere and see what you get. So, class, what's the only value that makes the top equal to 0? -8. X-intercept, -8, 0. Only -8 makes the top 0. That's why the x-intercept is -8, 0, because only -8 makes the top equal to 0. Find the y-intercept, plug in a 0 for every single x. You're left with 8 divided by negative 2. What's 8 divided by negative 2? Negative 4. That's how you find an x and y-intercept, everyone. X-intercept, what values make the top equal to 0? Y-intercept, which is not actually any different than it's always been. You plug in a 0 for every x. There are two numbers that make the top equal to 0. Two numbers. What are they? 6 and negative 6. Good. Why? Because if you use difference of squares and factor that top, you get this. Which is why our x-intercepts for this one are 6, 0 and negative 6, 0. To find the y-intercept, plug in 0 for every x. And what do you get? It's not always negative 4, but you do get negative 4 again. A lot to remember, I know. What we have right here, everyone, is an example of an interesting rational function, because the domain is every number except negative 5 and 0. But since 0 is not in domain, that means this graph has no y-intercept. If 0 is not in your domain, you can't have a y-intercept, because you're not allowed to plug 0 into the function. What actually happens is, it's one of our vertical asymptotes. So we don't ever actually touch the y-axis. That's okay. It's okay to have no y-intercept. This one doesn't have one. What makes this one interesting, though, is if you set the top equal to 0, you get plus or minus 2i. Can imaginary numbers be x-intercepts? Can imaginary numbers be x-intercepts? No. So this is a rational function that has no x-intercepts. It also has no y-intercept. So that can happen. You got to be ready that maybe it doesn't have one, or maybe it doesn't have the other. Maybe it has one but not the other. All right. So, that takes us to the part of the lecture of things we almost never see in Math 121. And by that I mean these are things that might show up on the homework but are not going to show up on your exam. So you might need to deal with these things, but they're not things that I directly test you over. But the problem is some of the homework is like these multiple choice problems, and they include some of this terminology, so we do need to talk about it. So let's talk about these two things here. So don't feverishly copy this down. Just know this is in your notes if you need it later, because it's a little bit wordy. Is this going to be on your test? No. Oblique asymptotes, everyone. We don't deal with these in this class, but you might see this term show up. We don't cover them in this class. However, you might see the term oblique asymptote show up in your homework, so be ready for that. Sometimes they call them a slant asymptote. So be aware that while you're doing your homework, you might see the term oblique asymptote or slant asymptote. Not on your test, but you might see them in the homework. Almost every rational function we encounter is not going to have one, but they might slip one in occasionally, and here's what they do. A rational function does have an oblique asymptote if the degree of the numerator is higher than the degree of the denominator. In other words, if there's no horizontal asymptote. If a rational function has a horizontal asymptote, then it does not have an oblique asymptote. So if you're doing your homework and you run across a problem that says, does this have an oblique asymptote? It does if the degree on top is higher. That's what you look for. And the reason I bring that up is because you're going to see some questions that don't have them, but they're going to ask you, does it have one, and you say no. So you're going to see that terminology, and I didn't want you to wonder what it meant. The other thing that's not going to come up in this class, but you might see on the homework, but it won't come up on your test, is holes. A hole shows up when you have a factor on the top and the bottom cancel. And what it does, everyone, is it creates one missing point on the graph. And it also keeps us from having a vertical asymptote there. So these are things you do not need to worry about for the exam, but I wanted you to be ready when you were doing the homework. If you see a homework question or two homework questions that just say, hey, does this rational function have a hole in it? Well, it does if you have a common factor that cancels. So I brought up some pictures here to show you what these look like, just so you're not completely lost, because that's not my intention ever. Here's something we're not going to be drawing in this class. There we go. Here's something we're not going to be drawing in this class, but what you see here, everyone, is a rational function that has a slant asymptote, a diagonal asymptote on it. How does it have one? It happens because the degree of the top is 2, and the degree of the bottom is 1. The degree on the top is larger. That's what creates a slant asymptote. There is no horizontal asymptote when this happens. This is not on your test. But be careful when you're doing your homework. Copy. I should really shrink these before I come to class. So big. Still so big. All right, here's one that looks like it has a hole in it. What happened here is you have a factor on top canceling the one on the bottom. The original rational function, just in case you can't read that, because that's smaller than I thought it would be, looks like this. And the x plus 2's cancel. What that does, everyone, is it creates one single missing point on the graph, called a hole. That's what happens when factors cancel. It also prevents us from having a vertical asymptote there. So what happens is the only vertical asymptote for this one is at x equals -5, not at -2, because there's a hole there instead. This is not on your exam, but just be aware it might come up in the homework. If you're interested about these things, it's not that we're trying to keep this a secret from you, it's just that these get taught in pre-calculus instead. What we're doing here is sort of an introduction to rational functions, and they worry about some of the more details in the next class. So you will learn about these. And now when you learn about them, you'll like say, Steve mentioned that, but we didn't go into a lot of detail. Cool? Let's look at a problem that we might see in this class. Let's look at one that's better for us. This problem I'm going to do right now is f of x equals x squared minus 6x plus 9 all over x squared minus 6x plus 5. Let me make sure that's the one I want to do. Just give me a beat here. No. We're going to do the other one. We're going to do that one that I said we were going to do. We're going to do 2x squared plus 12 over x squared minus 4. We're going to graph this. This is the one that I said I'd train you how to graph before the class was over. We're going to do it right now. All right. We got to be careful of that difference of squares. Don't just eyeball that bottom and say, I know you can't plug a 2 in here. Factor it as a difference of squares, because then you'll see that you also need to kick out negative 2. So the domain for this rational function is everything except negative 2 and 2. Those are the two numbers that will make you divide by 0. Those are the numbers we need to kick out of our domain. So far, so good? If those are the numbers they kick out of our domain, are those also going to correspond to our vertical asymptotes? We have two vertical asymptotes. This directly gives me my vertical asymptotes. And my vertical asymptotes are x equals 2 and x equals negative 2. So far, so good. Horizontal asymptote. The degrees match. Now, I don't expect you to have this memorized yet, but maybe someone does. When the degrees match, do we have a horizontal asymptote? Yes. Is this the one where it's always just 0, or is this the one where we divide? This is the one where we divide. So it will be y equals 2 over 1, the leading coefficient of the top divided by the leading coefficient of the bottom, or just y equals 2. And there's all of our asymptotes, both the horizontal one and the two vertical ones. We've got them. Next, x-intercepts. Set just the top equal to 0, just the top. Subtract 12 from both sides. Divide both sides by 6. I'm sorry, divide both sides by 2, so you get negative 6. And we have x squared equals negative 6. When I apply the square root property, what kind of zeros am I going to get? Imaginary. Do imaginary numbers correspond to x-intercepts? No. So this one actually, since I end up with x equals plus or minus the square root of 6i, means we have no x-intercepts. This graph will never touch the x-axis. I wonder if that's going to help us at all. Y-intercept. Think very carefully about what I ask you next. Did we kick 0 out of our domain? Did we kick 0 out? No, we only kicked out negative 2 and 2. So if you want the y-intercept, you plug 0 into the function and it kills everything except the constants. In this case, 12 and negative 4. Leaving us with negative 3 as our y-intercept. And that's about all we do before we start drawing a graph. Now, you do not need to feel like a pro at this today. You do not need to feel like the world's biggest champion with rational functions. If you feel like I'm keeping any of those things, domain, vertical asymptotes, horizontal asymptotes, x-intercepts, or y-intercept, a secret from you. That's how to find them. As I said, it's okay to be thinking, I need more practice with this, Steve. This is rough. That's all right. Now, I go to my graph, and when I do these, everyone, I actually find that with all those asymptotes running around, the graph gets a little bit sloppy if I do it on my traditional grid. So I just omit the grid lines and just do it on one of these. I find this is a lot better for these rational functions. It's a lot smoother, doesn't get as messy as quickly. So this is going to be my grid. I'm going to put my asymptotes on here. I'm going to put my asymptotes. I had vertical asymptotes at negative 2 and 2. And I had horizontal asymptote at y equals 2. And for the purpose of us all feeling okay about this thing, I'm going to go ahead and label every one of these so we all know what's going on. How many pieces is this graph going to have? 3 pieces. One more than the number of vertical asymptotes. The vertical asymptotes break up the graph. So because we have two vertical asymptotes, we're going to have three pieces to the graph. Make sure you draw a function. In other words, passes the vertical line test. We have to make sure we draw a function. Now this part's actually pretty cool, everyone. I know I have one ordered pair, and that one ordered pair I have is right here at -3 on the y-axis, because that's my y-intercept. I have no other ordered pairs. But I promise you this is enough to draw a picture of the graph, and I'm going to show you why. Let's start with our first piece we're going to draw. We're going to draw a piece to the left of this vertical asymptote over here. Graphs hug their asymptotes. They hug them. So don't do what I do yet, just watch. Our graph either is hugging the asymptotes up here like this, or it's hugging it down here like this. It's not doing both, because if it was doing both, it would fail the vertical line test. Does everyone see that? It cannot be both of those. So the question is it the top one or the bottom one? Why do you say it's the top one?
Because it has no x-intercepts.
That's right. Does our graph have any x-intercepts at all? No. And does that bottom piece look like it's hitting the x-axis? It sure does. So, can't be down here because no x-intercepts. And you can't just stay below the x-axis because you eventually have to get up to that horizontal asymptote. So it's got to be over there. All the way on the right side, is it going to be the same thing? It has to be on top because we can't hit the x-axis? Yeah, it has to be up here, hugging the asymptotes. Must also be up here because can't hit x-axis. Now, technically, are you allowed to touch a horizontal asymptote? Yes. So we cannot say that the middle, we cannot say that it doesn't look like this because of the horizontal asymptote. But we can say it doesn't look like that because, once again, what is this doing that it shouldn't do? It's hitting the x-axis again. It's having x-intercepts. So, once again, to avoid the x-axis, we must draw this piece down here. Is this a parabola, everyone down here? No, not a parabola. That's how we sketch a rational function, everyone. We did it. It's pretty slick, I think. I actually really like these problems. I like them enough that I think we're going to do another one right now. Is that okay with everyone? Bust out another one of these things. Okay. -2x over x squared minus 9. Another rational function for us. I would factor that denominator. That way you don't forget to kick out any values. It is very, very easy to look at that denominator and say x can't be 3, and that's it. But remember, x also can't be -3, because that will also cause division by 0. So our domain is going to be everything about 3 and -3. I'm sorry, -3 and 3. I should say it in that order. Once you know your domain, what do you get for free? You get your vertical asymptotes for free. Horizontal asymptote. Degree on bottom is larger. Who remembers what that means? Say again?
Has 1. 1 over.
One horizontal asymptote, where is it? Y equals
0.
0. Very good. If the degree on the bottom is larger, and I don't expect you to have this memorized yet, check your notes. That tells you that y equals 0 is the horizontal asymptote. It's right in there. Buried with a lot of other information, but it's in there. X-intercept. Set just the top equal to 0. Don't make this harder than it has to be. What value do you multiply by -2 to get 0? 0. -2 times 0 is 0. That means our x-intercept is 0, 0. And 0, 0 is also the y-intercept. 0, 0 counts as both an x-intercept and a y-intercept. So what do we know about this graph? We know where we have our vertical asymptotes. We know where our horizontal asymptote is. And we know that we have one ordered pair at 0, 0. So we're ready to start drawing a graph. Okay. Oh, come back here. All right. Let's see here. Wait a minute, where were they? 3 and -3, not 2 and -2. Okay. Okay, get my vertical asymptotes in here. And I know it's hard to draw a dashed line if you just drew a solid line, and I have the luxury of using different colors up here. So if you're having a hard time putting your horizontal asymptote right on the axis here, what some people do is they do like a little line above, a little below, above, below. Some people put them at a slight angle like that. You know, whatever you need to do to make it so you can see that there's a dashed line there on the x-axis is fine. All right, now here's the problem, everyone. Here's the problem. Our function is f of x equals -2x over x squared minus 9. Now, over here on the far left, the question is, am I up here or am I down there? And I can't use the same trick I used on the previous problem because neither of those touches the x-axis. Does everyone see that? So I need to figure out where this graph is located. Well, let's double check. We need to plug a number into the function that's smaller than -3. Someone give me a number smaller than -3. -4. Smaller than -3. I plug in a -4. And on top I get 8. And on the bottom I get 7. I get 8/7. Which piece is it, above or below? 8/7 is positive. And that's an ordered pair, everyone. -4, 8/7. So, should have rethought this before I did this. Here we go. That means we have an ordered pair right around here. And does that clearly tell us if we're above or below? Yeah, once we have that one ordered pair, we know we're above. So we just hug our asymptotes like that. Don't assume it's going to be the same on the other side. Don't assume it's going to be different on the other side. Plug in a 4 on the other side. And this one is going to give you -8/7. So we are going to be below on this side. You know, no matter how many fancy tricks you learn, and this works for any function you ever graph, no matter how many fancy tricks you learn, always remember, you can always find an ordered pair by plugging numbers into the function. Now here's the problem with the middle, everyone. There is a problem with the middle. I don't know for sure what it does in here because we could do anything with horizontal asymptotes. Don't do what I'm about to do, everyone, because I'm going to make a mess. Let's see if I can do my magic pen here. Is it possible that our graph looks like that, where it opens down on both sides and hugs the asymptotes? Yeah, it could do that. It's not really a magic pen, is it? Oh, it was a magic pen. It could be up there, like that, hugging both the asymptotes, or it could be down on one side, up on the other, or up on one side, down on the other. So we're going to need a couple of values. We need to figure out where this thing is. So what we will do is we will plug some numbers into our function, like 1 and -1, to get a couple more ordered pairs. If we plug in 1, we will get -2 over -8. If we plug in -1, we will get +2 over -8. So this is going to be 1 1/4 can be -1, -1/4. Which means we get this point right here and this point right there. Since we're never allowed to touch the x-axis anywhere but at 0, 0, once it's above, it stays above. Once it's below, it stays below. So this one must go up on this side and down on this side. Why did I want to do that one for you? Because that one's trickier. Because that one we couldn't just draw just from our 5 pieces of information: vertical asymptote, horizontal asymptote, domain, x-intercept, y-intercept. This one we had to actually find a few extra ordered pairs. Question?
So can I plug like any numbers instead the 1 and 1/4?
Well, what you want to do is you want to pick numbers that are in between your asymptotes where you're working. So you could have also picked 2 or -2. You could have also picked any other fraction in there, but why would we pick fractions if we don't have
The
to?
same thing, right?
What's that?
And it's gonna give me the same.
Well, if you put a 2 in there, you're not going to get the same thing, but you are going to get a positive number. So what we're really doing is I don't care so much about what the ordered pair is. What do I really care about? Whether it's above or below the x-axis. No one said these were easy. They are tricky. They are tricky. So when you're picking your x values, pick x values that are between or beyond the vertical asymptotes where you're curious about the graph. That's the secret, everyone. You want to stay in the area where you're working. Okay, a couple notes for everyone. You will need to graph one of these on the test. Once again, this is a tricky thing, so even though I'm going to do a couple more examples for you next time, I will tell you this. Well, first I'll write that. More examples next class. More video examples on YouTube. And a worksheet on D2L with answer key. So you do have a lot of resources for this. I don't have time to graph on one of those, but just give me a minute here just to talk to you all a bit candidly about these things. Because this section comes near the end of the unit, a lot of people don't do well with it on the exam because they're just not ready for this big thing that comes right at the end of these rational functions. Unfortunately, it has to come at the end because we need to build up to it. But I will tell you that you want to practice these as soon as possible and get your questions answered as soon as possible. And that means either talk to Rachel about these, go to her session and do a couple of these with her. Even if you don't do the full graphs, just do some examples with her where you find vertical asymptotes and horizontal asymptotes, just so you can find those. Come to my office hours, talk to me about it. In case I didn't make it clear, I love this stuff. And I'd be happy to show you some more information about these things. So what we're going to do next time, class, is next time we will graph more rational functions, so I'll give you some time to digest this, and we will cover section 3.6. So do me a favor.